So the last thing we were doing is we talked a little bit about, well, I give you examples like these Diophantine equations, x squared minus 10y squared equals 2. We reduced this mod 5 and showed that this equation that could potentially have infinitely many solutions actually has none at all. One of the real powers of modular arithmetic. So, theorem. If P prime and P does not divide A, then A to the P minus 1 equal to 1. This is called Fermat's little theorem, opposed to the Latin one. And this is actually kind of a central thing, well, all over the place, right? I mean, it's used coding theory, and it's kind of the basic structure thing. Let me actually give you a little bit more a general theorem from which to follow, and I'll put this off as a proposition 3, 2, 5. If A is in C and P is prime, then A to the P is equivalent to A mod P. Okay. Might take a little side of this. I'm familiar with this, although probably everybody is. How many of you have ever proved this particular thing? Right, so yeah. So let us consider now, I don't know much, but this is sum k equals 0, A to the K. Times that binomial coefficient. Now, this is A to the P plus 1 plus the sum k equals 1 to P minus 1. Choose K. Times A, of course. And what's the magic that makes this work? The P choose K. The binomial coefficients in the middle, right? I mean, the ones that don't correspond to 0 or P are all divisible by P. And prime is very important here. Aside for K between 1 and P minus 1, PK is a multiple of P. And what I'm gonna do is I'm gonna actually use another thing that I'm not gonna prove, and that is this is an integer. But there's a number of ways to see this, right? I mean, obviously it's the coefficient it's P cubed K, there's a number of ways to see this. But if you look at P choose K, this is P factorial, K factorial, P minus K factorial. And this is an integer, so I'm gonna call this R in Z. That actually is natural number. So this means that P factorial is equal to R times K factorial times P minus K factorial. Now, this is kind of the neat definition of prime here. Clearly, and I really didn't be clear here, P divides the left side of this, correct? So it must divide the right side, right? So we've got three such, actually, we've got this whole incredible long thing, but let's just look at these three factors here, R, K factorial. P can't divide this. Can somebody explain why? K is less than P, and P is prime, right? So since K is strictly less than P, K minus one, all these things, they can be factored into primes, and those primes have to be strictly less than P. So, and there's no way P can divide something if it doesn't divide one of the elements of the product, it divides none of the elements of the product. And because K is between 1 and P minus 1, this thing is between 1 and P minus 1 as well, so you get the same problem. That means that P divides R. And this is exactly what I wanted, because this means that these are all multiples of P. So this is equivalent to A to the P plus 1 mod P. Right. So now that we've got this, so what we have at this point is that independent of A, we have A plus 1, the P is equivalent to A to the P. Okay, so now I'm going to do induction. If A equals 1, then A to the 1, or I'm sorry, then 1 to the P is equivalent to 1 mod P. No problem there, right? Now suppose this holds for some K greater than or equal to 1. So we have A to the K is equivalent to A mod P. A to the P is equivalent to. There we go. K to the P is equal to K mod P. Assume that's true. Now consider K plus 1 to the P, our little limb over here, is equivalent to K to the P plus 1. And by induction, this is equivalent to K plus one. Right, because this is equivalent to K, and one is equivalent to one mod P. And so there we got it, all right. So we have a to the P is equivalent to a mod P. For all a greater than or equal to one. This is clearly true for 0. And it's clearly true if you multiply or if you replace a by negative a, even in the case for 2, because there's no distinction between plus or minus mod 2. So that wraps it up for everybody. And of course, to get back to Fermat's little theorem, so we have while a can see a to the P is equivalent to a mod P. And this, of course, a translation of this is a times a to the P minus one minus one is a multiple of P. So if P does not divide A, then P divides A to the P minus one minus one. Therefore, A to the P minus one is equivalent to 1 mod P. If P is divided. By the way, for those of you, how many of y'all have had 8520, the second semester read it out? So this might look familiar because Z mod P, finite field of P elements is the splitting field. Of X to the P minus X. Right, which is essentially that right there. And if you don't know what that means you should be with me next semester, right? Okay. Voltage on this. This is Theorem. This is my favorite theorem with a snarky name. Anybody know what this is called? The freshman's grade. That shows you that researchers do also take their teaching seriously. And having taught artificial calculus many years, let me tell you, the freshman dream way bigger than this. But anyway, so if you've ever graded a calculus, you will come across this at one point or another. You know, I really am more optimistic about students than that, because they write this stuff down. And I don't think it's because they really think it's true. I think the reason they do it is because I can't solve the problem if I actually have to put all those middle terms in, but I can solve it if I do it this way, so anyway. So let's prove this. For n equals well, it's certainly true for n equals 0. For n equals 1, we get a plus b to the p is equivalent to a plus b mod p by previous. Right. Now what you want to do is assume, actually doing this in terms of homomorphisms is actually pretty quick, but let's assume that a plus b to the p to the n is equivalent to a to the p to the n plus b to the p to the n on p. And now let's just ramp it up. A plus b to p to the n plus 1. We got to make sure this works. Any ideas? Any prescriptions? Maybe some cowbell.
Right, that is a plus b to the p to the n to the p.
Okay. Same thing here. And here's where we can apply the inductive hypothesis. And here's where we apply the base case, right? So that's a really groovy result, I think. Okay, so that should probably take care of sort of practice for this. And now we're going to kind of move into some more modular arithmetic. So we're going to do a little modular arithmetic here. Let's start talking about the Legendre symbol. How many of you have encountered the Legendre symbol in your travels? Well, yeah, that's pretty good. How many of you have seen quadratic reciprocity? Okay, wow. How many of you seen it proved? Does anybody remember how you saw it proved? I think that there's something like 105 different proofs in the literature. It's a ridiculously large number, right? Well, obviously I've got my choices, but we're gonna use Gauss sums actually. How about the symbol itself? Well, so consider the equation. So suppose I give you the challenge to solve this equation, right? P is some fixed prime and A is just some number, right? So it might be, for example, x squared is equivalent to 7 mod 19, or x squared is equivalent to 3 mod 5, whatever I want. Basically, what this question is asking is, mod 19, is this thing or is it not a square, right? And it's asking the same thing here, you know, is 3 a square or is it not? Mod 3, or I'm sorry, mod 5. So let me point out something. If this thing has a solution, we say A is a quadratic residue. Mod. Now, let me point something out here. This might be useful. Let's look at a decent sized problem like 19. I'll use, and oftentimes I'll disregard zero because mod P, zero is the only zero divisor. Everything else is the n. Suppose I wanted to look at what the quadratic residues are. Let's make this clear. So, what are they? 1, 4, 9, 16, 25 is 6, 36 is 17, 49 is 11, 64 is 7, and 81 is 5. And look at me, I ran out of board. I guess I've got 9 others to check, don't I? Or do I? Actually, what's the relationship between 10 and 9 mod 19? That's right, 10 and 9. So this would work for 10, 11, 12, 13, 14, 15, 16, 17, and 18, which is -1. So notice in Z mod 19, there are 18 units, right? Because the non-zero elements form a group. And in fact, we know from an earlier result in class, a cyclic group. So you've got the cyclic group of order 18. How many of those were squares? Half of them, right? By the way, what would happen? So here we've got a cyclic group of order 18. And I'm asking myself this, what are the squares? Turns out it's half of them, right? What if my cyclic group were odd? How many of them would be squares? Well, so if I ask you this, so suppose I've got a cyclic group of odd order under multiplication. And I ask myself this, so how many are squares? All of them, right? All of them. Right? Because certainly every even power of the generator is a square. But so let me kind of throw this in just for fun. G is cyclic. And the order of G is 2n plus 1. How many elements of G are squares? That's my big question. Well, notice that certainly all the even power are, but everything's an even power, right? Let G equal X. That's the generator. Right? Notice that X to the 2n plus 1 is equal to the identity. Right. That means that X to the 2n plus 2 is equal to X. But this is X to the n plus 1 quantity squared. So even the freaking generator has a square root, right? Because you're asking about squares in an odd order group. That means that everything's a square. Because if the generator is a square, every power of the square is a square. Right? Now, mod P that really makes life boring, right? Because the only prime, because remember, we're looking at prime, the only prime whose multiplicative group has odd order is 2, and it's got order 1. What a shocker. Everything is a square, right? However, this does extend to finite fields of characteristic too, right? If you've got a field of order 4, if you've got a field of order 8, which these things certainly exist, then their multiplicative groups are cyclic of odd order. If you have a finite field of characteristic 2, everything's a square. And by the way, if you have a finite field in general, it's not true that everything's a square. I mean, here you go. But everything is the sum of 2 squares. That's my thing. I pick anything. 2 is this plus this. 3 better be in there somewhere. Let's see. I guess what do I need for 3? I get like 22 or something like that. Here we go. This plus this. Turns out that anything is a sum of 2 squares in a finite field. This is something to keep in mind. This is with regard to this little equation we're trying to solve. If P is 2, then everything's a square. If P is odd, then half of the non-zero residues are squares, and the other half of the non-zero residues are not squares. So let me formally give you the definition of the Legendre symbol. So definition. And yeah, I'm gonna do this for non-prime. Definition. Let's give you an odd prime. And A in Z mod P. Here in this section, Z mod, that notation, I know there's some p-adic fans out there. This means the integers modulo P. Then the Legendre symbol mod P is denoted. Yeah, it looks kind of like a binomial coefficient there. And it is given by one if x squared equivalent to A mod P has a solution, minus 1 if x squared is equivalent to A mod P has no solution, and let me correct this, 0 if P divides A. This right here is the P doesn't divide A case. So some people actually define the Legendre symbol just for these two, and they ignore the case where P divides A. They say, okay, you have to have a non-zero. That is, A is a non-zero element of Z mod P. That is, A doesn't divide P. But here I'll embrace kind of a broader definition. So, for example, as it turns out, the 2 mod 5, if you look at 2 mod 5, this is non-square. Notice, of course, 4 is the square mod any prime. Well, yes, yeah, any odd prime, prime P to be odd. It's -1. But, so for example, 11, 19 is 1, because that is, right? So there should be something interesting about this. So let me make the following observation. Here's a. In this theorem, we're going to let P be an odd prime. And I'm gonna be. And let's suppose that AB let's assume that these are non-zero elements. Number one, if A, B are quadratic residues. So is A. Not too surprising, right? If A is a square and B is a square, then A times B is a square. 2, if A is a quadratic residue and B is not, and AB is a quadratic non-residue. Again, no surprise, I don't think, because A is a square, B is not a square. I wouldn't expect A times B to be a square, and that is indeed the case. 3, if A and B are both quadratic non-residues, AB is a quadratic residue. This might be a little surprising because what it says is if you have the product of two things that are not squares, all of a sudden their product is magically a square. You generally don't see this happen in fields, right? So for example, in the rational numbers, right? 2 is not a square, 3 is not a square, 2 times 3, not a square, right? In fact, it's possible for 2 non-squares to be a square, but it's pretty rare. 2 is a non-square and 2 is a non-square. 2 squared is a square, right? But in general, you don't expect it to happen, right? Why does it happen here? Why does it have to not be? And this is really kind of one of the real reasons why we consider this. Let's go through the proof of this. 1, A equals x squared, B equals y squared, AB equals xy squared, right? That's true in general, right? So no problem first. Let me do 3 first. The product of the 2 non-residues is a quadratic residue, and this will give us insight to this one as well. Right, 2 is, you have to think, I mean, 2 is kind of interesting as well. Well, actually, I have to do that in the field here. Yeah, you know what? I'm a liar, pencil fire. I'm gonna do 2 here. 2, this is true. in any field. If both A and B are non-zero. Right, this is true in any field, so is this, because suppose A equals X squared, B is non-square. Suppose AB is a square. Just for giggles. Well, A is X squared and B is just go B. And so since this is non-zero, I divide it, so B is Y over X squared, which is a contradiction. So maybe it is right, that it shouldn't be so surprising, because that's true over any field. What about 3? This is the part that just really, I mean, I've given you a counterexample for the rationals, for example. 3 does depend heavily on our setting here. Suppose A, B are non-squares. Now, ZP star is generated by X. And the order of X is 2, and 2n, of course, is P minus 1. So we know that the multiplicative group of a finite field, namely ZP in this case, is cyclic, it's generated by X. And since P is odd, P minus 1 is even, and so this must be an even ordered group, right? Now, I don't know much, but I know that if A I know that there's no way it can be an even power of the generator, because if it's an even power of the generator, it's a square, right? So I know this. A is 2 is X to the 2t plus 1, and B is Y, or no, it's X to the 2s. That's the only way that these things can be non-squares. They have to be an odd power of the generator. Now multiply. AB is X to the 2t plus 2s plus 2. This thing is even, so this is Y squared, some Y. Namely, Y in this case would be X to the t plus there, it's an S. Should be t plus f plus 1. That's what Y would be. Okay. Any questions on that? Questions so far? Okay, so here's a warm up too. Let's see. Example. Let's do a linear equation first. How will we solve this?
Find the inverse of 4 mod.
Right, I mean, that's what you want to do, right? I mean, 4 is not 0 mod 103, so it's got to have an inverse. So the question is, how do you find that inverse? Big practical point.
26.
What's that?
I think X is 26.
Yeah, it should be,
The basic coefficient.
I think it's 26, isn't it? Or am I wrong?
Because 104 is 25.
So here's the deal. What is for inverse mod 103? Well, so what you're trying to do is you're trying to solve now. 1/4 is too confusing for my pea-sized little brain, so let's do that. Right, and in fact, if this didn't work, I could just keep kicking it up by multiples 103 until, notice this one is divisible by 4, right? Should be 26, right? Which is equivalent to 1/4. I mean, that's what it is, right? And so multiply both sides of this by 26, and I get x is equivalent to 286 mod 103. I multiply that by, so you did. And let's see, is that 206? So that's x is equivalent to 80 mod 1. So there you go, and that works, right? Because 320 minus 11 is 309, which is called 103. Okay. How about this? Okay, let's set the voltage and then like we're in algebra 2 and do some quadratic equations, right? When can we solve this? By the way, I should turn the sound up on that before you see, when we ask my graduate students, if you remember what the quadratic equation is here. Somebody tell me why the quadratic equation is going to work here, just like you did it when you were in high school, it's going to work here. Why?
Well, the division exists, the square root exists apparently.
Well, so the square root is the hump we've got to get over, right? But what's the division problem that you're putting your finger on? Yeah, you do your magic, you go x equals plus or minus blah, 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 divided by, in this case, 2, right? Mod 7, you're okay. The quadratic formula falls apart in characteristic 2. I mean, you can certainly extract roots of polynomials, but that formula is not going to work anymore. But mod 7, you're good to go because you can divide by 2, just like you can divide by 4 in mod 103, right? So, in fact, the way you would derive the quadratic equation is exactly the same as you would when you're teaching an algebra 1 class in high school. You would complete the square, everything you do is kosher, and since you've got division by 2, you can do all that stuff. And so what I would get if I solved this was x equals, in this case, negative a plus or minus the square root of a squared minus 4b over 2. So this is gonna give you, so again, if you've had 8520, this is gonna give you two extensions, some field extension, because you can divide by that, and the square root. You can make a field extension if you like. However, what's the solvable? Z7, this needs to be a square, right?
Well, I guess we've also showed that every. Okay, so in. What we, the inverse of squaring sort of is plus or minus square root, the numbers reduced to. Yes, we have to think if there's any more other than just a plus or minus. You know, if a square root of it exists, that's truly, they call the inverses of squaring.
Well, so basically, so think of it this way. Think of this. In P mod 7, 1/2 is equal to. Yeah, that's right. It's the same thing over here. So my formula is now x equals negative 4a plus or minus 4 times the square root of a squared minus 4b. Now, the question that you probably want to ask yourself at this point is, look at this junk. When is this in Z mod 7? 4a, no problem, right? 4 times something, no problem. Here's where the problem is. The question is, when is, so solution in Z7, if and only if a squared minus 4b is a square. And so, let's kind of do my naive little thing again. I guess a squared minus 4b could be 0, but the double root what you usually do. 1, 2, 3. I'll let this out explicitly. 4, 5, 6, because there's not that many rows. And these square to 1, 4, 2, 2, 4, 1. So this is solvable if x squared, if a squared minus 4b is equal to 0, 1, 2, or 4. Otherwise, it's not solvable without, it's not solvable within the confines of Z mod 7. Let me give you the statement of quadratic reciprocity, which will give you something fun to play with over the weekend. You know, so much of this. Theorem 416. Let P be an odd prime. Zero odd prime. Then, 1 AP is equivalent to A to the P minus 1 over 2 RP. Number 2, AP BP is equal to ABP. And 3, this is statement of reciprocity, I got over excited. If A is equivalent to B mod P, then the symbol AP is equal to BP. Right, so these are kind of some facts here. Verify these. This one follows basically from a previous statement. This is very easy to justify, I think. The most interesting one is, of course, the first one. See if you can figure that one out. Okay, it's a good place to quit. Any questions? Well, I hope you all have a great weekend. I hope to see you in the math club this afternoon. Other than that, I will see you on the next day of the start weekend.